So today is the last lecture of parametric resonance. And we start with the, actually we finish with the example of the pendulum with the vibrating support. So remember, we had a pendulum, the usual model, but the difference is that the support is moving in a prescribed way, which is periodic motion. So with some period t capital. So what we know is that equation of motion can be written as phi double dot plus I can put it together as g my plus the gravitational acceleration plus acceleration of the support divided by L sine phi equals 0. And then you linearize it near the equilibrium phi equals 0. So in that case, sine phi can be approximated by the angle. And then you get the linearized equation. So this is linearized equation. And the next step, what we did is we considered the position of support is such that its double derivative, second derivative is, so it's omega delta squared. So omega we define together with t. Period also defines always the angular frequency, right, by the standard relation. Okay, and then we consider acceleration on the first half of the period as one value and the opposite value and the second half of the period. Which gives you the position of the support. It looks like sinusoidal. Its first half of the period, it's parabola up to t over 2, and another parabola up to t, and so on. And the way we have chosen this h double dot is so that this amplitude is proportional to delta. So in that case, it will be delta by some constant which is close to 1. Not so far to 1, close to 1, and then it's minus delta p squared over 8. Something close to 1, to delta. So it goes delta up, delta down, delta up, delta down, delta up, delta down. And then finally, we made a change of time so that we reduce the system to some standard form. So we use the time tau, which is omega t. Yeah, omega t. So then, in that case, the period become because of this relation, period is becoming 2 pi. Right? Then also we define value a, which is coming from this, so j over L omega squared. C is dimensionless variable. And then also B is delta over L, which is, you see, delta over L is a relation between the amplitude of the support to the length of the pendulum. So usually we will consider delta small compared to L, so B will be small, and A can be small or large depending on frequency. You see, because L is small, but frequency can be large. So this gives you Masonry equation. Which is d to phi b tau squared plus a plus bh of tau phi equals 0. And then there is this periodic function h. It's just 1 in the first half of the period. And period is pi, right? So 1/2 period is pi, full period is 2 pi. And then it's 0 in the second half. And continues periodically. So our function h capital, which stands for this, comes from this double dot. So it's just 1, minus 1, 1, minus 1, 1, minus 1, and the points p, 2 pi, 3 pi, and so on. So that's a equation which, after change of coordinates, describes the pendulum. And our equation is the stability. Stability analysis. So essentially what we want to know if we don't move the support, pendulum is stable. This we know, right? So the question, if we start moving support up and down, can it be stable? When it will be stable, when it will be unstable? So under which conditions this happens? And we had a lecture on the general theory last time. So what you have to do, you have to go to the phase space, right? So consider the vector of the coordinate and velocity. And then we write equation for derivative. So derivative is what? It will be phi dot, phi double dot, right? And this is some matrix by x. So x, what is, remember, phi dot. So from this, you can find the matrix G. So the first, you should get phi dot. So in order to get phi dot, you just put 0, 1. Right? So when you multiply this matrix by this vector, you get phi dot. And phi double dot is this term. So it should stay here, minus a with a minus, right? Because we put it on the other side, minus b h of tau. And here 0. So you can see that this equation just can be written in this form. So it's g of tx. So we have equation at the end, which is x dot equals g of tx, exactly the linearized system that we considered last time. And for this linearized system, we know how to detect stability or instability. So what you need is you need to find a flow K matrix. So for K matrix F, we found out that this is exactly the. So what flow K matrix does, it moves. It moves the initial point to the point after a period, by definition. So the meaning of flow K matrix is F when you apply it to initial condition, it becomes x at points 2 pi. So this definition of the flow K matrix is just moves. Remember this picture of the Poincare section. So we have this space, and then we have a period. In this case, it's 2 pi. So whenever point x at 0 you take, then our function f moves it to the point x at the period. So this is function f. So we need to compute it for the system. And what we do, Usually, computing so finding solutions of differential equation with periodic coefficient is difficult problem, but we know how to find the solution if the coefficient is constant. But the coefficient is piecewise constant, so it's constant on the first half of the period, constant on the second half of the period. So on half period, we can solve it. And this is what we do. So the way you solve it, you put one more section. You put one more section at half a period. And then you define the function which just move it on a half a period. It will call it function f1. And then we define another map which moved this initial condition to another half a period. So it must go to the same position, right? So and we'll call it f2. So in other words, we call f1 is the matrix which applied to initial value gives you x at half a period, and we call f2, which is, if it's applied to any initial condition at initial moment pi, then it gives you the value at 2 pi. So now you can combine everything. So you can say that f x at 2 pi. On one hand it's f of x0, but with new matrices you can first write f2 x at point pi, and then using the first expression you write f2 f1 x0. So you see the relation f equal f2 f1. So if we find matrices f1 and f2, we are done. So we need to find this matrix and that matrix. And then the product of matrices give us Floquet matrix, and that's what we also remember, that stability condition was the eigenvalues of this matrix F. In the case of stable situation, they have to be inside the unit circle, and unstable, so this is real part of eigenvalue, imaginary part of eigenvalue. This is from yesterday, where rho is the eigenvalue of matrix, Floquet matrix. So for the stability, you need all the eigenvalues to be inside, or some of them can be on the boundary of the unit circle, but they have to be semi-simple. And for instability, at least one should be outside. This leads to instability. So this is for linear system. This is stability condition for the linear system. And there was also asymptotically stable case where all the eigenvalues should be just strictly inside the unit circle. So this is a program. So this is what we have to do. And just we will do it. We'll do it. So let's see. Where were my notes? Okay. So what we will do, we will first we'll consider the case of small amplitude of the support. Let's better give the condition continue the case when A is bigger than B. We have two parameters in the system, A and B. We consider the B is smaller. So for example, it's small amplitude of the support. So you see, if amplitude of the support is small, then delta is small, then B is small, right? And A is something. So if delta is sufficiently small, it will be smaller than B. So we take a pendulum and we just move it slowly. Not slowly with small amplitude, just slightly. Good. So what then? Then A plus B and A minus B are both positive. So we can define omega 1 squared as A plus B and omega 2 squared as A minus B. Both are positive, right, for this case. And then what we do, we consider the situation, the situation when time is between 0 and pi. Consider the first half a period between this moment and that moment. In that case, H capital is just 1. So you can put 1 here. A plus B gives omega 1 squared. So the equation of motion becomes d2 phi d tau squared plus omega 1 squared phi equals 0. And this we know how to solve. Then we can solve it as phi equal A1 cosine omega 1 t plus B1 plus A2. How we did it. So we can take any linear combination of sine and cosine with two arbitrary coefficients. So the first coefficient we put A1, and for the second coefficient we put A2 divided by omega 1. We can just put A2, but then the final formula will be not so nice looking, so we can just as well divide it by omega 1. So because A2 is arbitrary, so it doesn't matter. Then we also can compute derivative. So this is all tau, right? So this is all tau. We took derivative, so this will become minus A1 omega 1 sine. And when you take derivative, omega 1 cancels here, so it will be A2 cosine omega 2 tau. Very nice. And then what you can write is that x at any tau is this vector, right? And then we can write it with the coefficients A1, A2, A3, and put cosine signs inside the matrix. So it will be cosine omega 1 tau. Here it will be sine omega 1 tau over omega 1. Here will be minus omega 1 sine omega 1 tau. Sine. You don't follow very well. Omega 2 omega 1 tau by A1, A2. So this is a general solution. And now what you do, compute x at 0. X at 0, you see this is 1, this is 0, 0, 1. So it will be identity matrix, so it's just A1, A2. And then also we compute x at tau, x at pi, x at pi. So you put just pi everywhere. A1, A2, but A1, A2 is x0. Then we compare this formula with what we wanted to find. So it's exactly that formula with the matrix is F1. So we find the matrix. So F1 is exactly this matrix. Good. So we are halfway to the answer because we also need F2. But the difference between F1 and F2 is just is that in H capital instead of it's -1. Right? Don't really look carefully. You know? So it's 1 minus 1, so H become -1, so it become A minus B. So instead of omega 1, you take omega 2, and the analysis is the same. So you get F2 just the same way, but with omega 2. Because just the same system, but with different frequency. And F, just take a product. First F2, then F1. So if you take a product, not very complicated, you find the full matrix F, which will be rather complicated 2 by 2 matrix. But 2 by 2 matrix, you can find eigenvalues. There is a formula because it's quadratic equation, and then you can see where they are placed inside the unit circle, right? So inside or outside. So that's program, and that can be done analytically, but better instead of doing this in a direct way, you can do it in a slightly more clever way. So what you can notice that if you take determinant of matrix S1, so what you get? You get cosine squared, right? Plus, because it's minus, so it will be plus omega 1 cancel, so it will be plus sine squared. So cosine squared plus sine squared, which is 1. Right? And there is no difference, so it's just the same for the other. Determinant F2 is 1. And then you have to remember that from the linear algebra, the determinant of the matrix product is the product of determinants. So it's determinant F1, 2 by determinant F1, which is, again, 1. So all determinants are 1. And then another thing that you remember from the linear algebra is that determinant of the matrix is equal to product of eigenvalues. A product of eigenvalues. Right? And in that case, now in our case, we have 2 eigenvalues because 2 by 2 matrix. And so the product is 1. So we know that if you have 2 eigenvalues, rho 1 times rho 2 is 1. Or you just, if you have one of them, you know the other. And this is a very convenient property. This is just one property. So the second property, which also you may remember from linear algebra, is that the trace of the matrix, trace the sum of the diagonal elements, is the sum of the eigenvalues. Okay. So we have a product of them is 1, trace we don't know, but now what we can have? So we can have 3 cases actually. Case A, when eigenvalues are real and different. So rho 1 and rho 2 are real, and rho 1 is not rho 2. So how is this possible? For example, this is the real part of imaginary part. So one of them will be here, another will be here. So we have 2 real eigenvalues. Their product should be 1. So if one is inside the unit circle, another should be outside. So immediately there is eigenvalue with real part. With its real part in that case is just, what means real part? With absolute value bigger than 1, right? Because if one is inside, another is outside, which means instability. Instability. And this case, in fact, let's see what is, we will want to use this trace condition. So if this happens, so what happens with the trace? So in that case, so both of them are real, so then absolute value of the trace, so let's take square root. Since both are real, we can just open the square in the usual way. So this will be rho 1 squared plus 2, 1 rho 2 squared. Then we can use the fact that rho 2 is 1 over rho 1, so it will be rho 1 squared plus 2 plus 1 over rho 1 squared. Okay. Yeah. And this you can add to and subtract to, so it will be no, it's bigger than 2. Okay, what we do, we add 4 and subtract 4. Take 4. And then you can check that the rest can be written as rho 1 minus 1 over 1 squared. That should work. So you see that rho 1 squared, rho 1 squared, 1 over 1 squared, and then there will be 4 minus 2, give you 2. So that's bigger than or equal to 0. So this is, actually this is not bigger or equal to, this is strictly bigger than 0 because this is rho 2, this is rho 1, and they are not equal. So this is strictly bigger than 0. So it means that this is bigger than 4. So we found that in this case, the trace, take a square root, should be bigger than 2. So the case A, it's unstable. And in this case, the trace is bigger than 2. So that's the first case. So case B is when eigenvalues are complex. So imaginary part is not 0. So that situation when So remember, when they're complex, one of them is raw, another is complex conjugated. At the same time, one is 1 divided by another. So you can see that the only situation that they can be conjugated and also one should be inverse of the other is when they are exactly on the unit circle. See, any pair on the unit circle, their product gives you 1. Yeah, because when a product of two complex numbers which are completely conjugated is a product of absolute values, which is 1. And then you should add the phases, which are opposite. So it gives you also 1. So in this case, rho 1 is complex conjugate of rho 2, or better, let's write the way around. And both of them are on a unit circle. Also, they're different. And by this criterion, we see that this is a stable situation because they're on a unit circle and they're all simple. So this is stability. So in case B is a situation where everything is stable. And also, we can find what is a trace. Better, I will write not this, but so in that first case, the trace of the matrix was bigger than 2. This is condition that we found. And here the sum of them, rho 1 plus rho 2, they're complex conjugated. So if you take a sum, imaginary part cancels, and the real part will just double. But real part is smaller than 1. So that should be smaller than 2. So you see that in that case, we get opposite conditions. So the trace of F is smaller than 2. So there is a second case which is stable, and in that case, trace is smaller than 2. And then finally, there is a case C. Well, case C is that they are, so you see case A, there's a real distinct case, and different case B, they were complex, and in that case, they're also different. So the only case which is left is where they're equal. This is the only case which is left. And if they're equal, you see that their product, which is the same as rho 1 squared, is 1, which means that there are two situations, that rho 1 equal rho 2 equal 1, or rho 1 equal rho 2 equal minus 1. So this is the only situation left. So either they both here, or they both at minus 1. Right? Or both meet here or meet there. So there are three cases, 2 real or different sides, unstable, 2 on the unit circle stable, and 2 met together. So this is case this means that they are multiple. So this, in that case, remember, stability depends if they're simple or semi-simple. Stability is on a type. Simple, semi-simple or not. It means Jordan block. So the question that depends if it's semi-simple, then we know it's stable. If it gives a Jordan block, it's unstable. So that's criterion, that's Floquet's theorem that we saw before. But that case is actually not, it will be a boundary case, so that's not so important. In that case, if you take also the sum of the eigenvalues, it will be 2 or minus 2. So the absolute value is 2, which is mean that one more arrow. It's everywhere was absolute value of the trace, right? So in that case, absolute value of the trace is 2. So we classified all three cases: instability, stability, and then there's boundary case. And what we also found is that you can distinguish these cases just by looking at the trace. So if the trace is bigger than 2, you know your case A. If its trace is smaller than 2, you know it's the case 2. And if case is equal to 2, you know in case C. So that we can make a summary. So if trace F there is no absolute value here. Okay. So if the absolute value of the trace is bigger than 2, you have instability. If the absolute value of the trace is smaller than 2, you have stability. And if the absolute value of the trace is 2, it depends, but actually this will be boundary between stable and unstable case. So this will correspond to stability boundary. Usually it's not very important what happens exactly on the boundary. It's important that boundary separates unstable and stable situation. Okay, so that's our summary. And now we just check it directly. So we know the matrix F, which is a product of these two matrices. And you can just compute the trace. So we don't need to compute the matrix, the whole matrix. We just need to compute its trace. So trace is the first element of the product plus the second. So its trace will be this column by this. We compute trace of the product, right? So its first element will be first column by the first row, and then there will be second column by the second row. Okay. So this by this. So let's compute. So this will be its trace of F2 by F1. It's trace of. So what will be this product matrix? So this value we are not interested. This value will be first F1. So F1 will be this column by this row. So it will be cosine omega 1, cosine omega 2. And then this by that minus this. That value is not interesting. And this value will be this column by this row. So first will be omega minus omega 2, omega this, then it by this. So then we take a sum. So this term is the same as that, so it's just twice. And then it will be minus with these prefactors, which are different, right? So it's omega 1, omega 2, plus omega 2, omega 1, sine. That's it. So what's left is just to see whether when the trace is big, more absolute value is bigger than 2, smaller than 2 or 2. And this, of course, depends on parameters. This depends on parameters A and B. And now remember what is A and B. So A and B gives you omega 1 squared is A plus B, and omega 2 squared is A minus B. This is what was it. And then also remember what is A and B physically. So A was what was A? G over L omega squared. Gravitational acceleration, L by squared frequency, B is just difference between amplitude of support divided by length of the pendulum. So first let's consider this condition for depending on A and B. So the simplest case is that consider B equals 0. First, consider B equals 0. B equals 0 means that support doesn't move. So delta is 0, so support doesn't move. So we are back to the usual pendulum. With fixed support. Then we can get stability, right? So we expect this to have stability. And then, so let's check that in that case everything is OK. So in that case, omega 1 equal omega 2, right? And equal A. So put it here. You will get the trace of F is 2 cosine AP. No, square root of A. Omega squared square root of A. B squared. And then this will be again 2. It will be minus 2 sine squared. Good. So cosine squared minus sine squared, this is what you remember what it is. It should be cosine of twice the argument. Okay. And we see that it's smaller or equal to pi than 2, right? No, that the absolute value of the trace. Did I write it? Yeah. In the notes, I forgot to put modulus several times. So just check it. Nobody complained. Trace of F is smaller or equal to 2 because cosine is not bigger than 1, right? So we are either at the boundary in a stable situation or in a boundary case. So that's that's in agreement with what we know with usual pendulum. It's stable. But now, what is important is for us will be the point, what's what we call resonance point. Points. The resonance points are where the trace is exactly equal to 2, which means that we're not far from instability. It's just enough to change trace a little bit, you will become unstable. So resonance points in where the trace of f absolute value is just 2. And in that case, what you see, in that case, when it's equal to, when cosine equal 1 or minus 1, which means that the argument should be integer number of pi, which means that 2 by square root of a should be integer. Is integer. Okay. A is positive, which means that a is a square integer number divided by 4. This is how you find it. So where n is 1, 2, 3, so integer number. So we found this resonance point. And what this means? It means that whenever you consider the plane of the parameters, so we put parameter A here, parameter B here. So whenever you're at B equals 0, so B equals 0 line, there are special points. There is one point where A equal 1 divided by 4. The next special point will be 2 squared over 4 squared. It will be 1. Oh, no good. Let's put it 1 over 4. The next point will be 1. The next point will be 9 divided by 4, and so on. So this type of point. So these are special points. So we made the instability analysis on this real line because B equals 0, and we found that these are special points where the trace is exactly 2. So it means that whenever B is becoming non-zero, what happens here in between will remain to be stable, right? But here we can have some instability. So we can just check it directly. So consider which point? Consider the first resonance point. 1 over 4. And let's just check small perturbation. Let's add, I'm giving just a perturbation which I like, because it gives me a simpler computation. So I take A plus some small number, and then B equal epsilon over P. So what I'm considering perturbation from this point, something like this. So as I move epsilon equals 0, you're here, and then epsilon positive, you're going in this direction. So let's check if it will be stable on this line or unstable. So what will be the trace? So in that case, omega 1 squared is a sum. And this is nothing else as 1/2 plus epsilon over pi squared. You can check. right? So it means that omega 1 is 1 over 2 plus epsilon over pi. And you can check that when you put minus here, right? Here minus will come with a minus. It just gives minus there. So omega 2 will be 1/2 minus epsilon over pi. Good. And then how we compute a trace? So then we compute this expression. The trace of f cosine with 2. Then it will be cosine pi over 2 plus epsilon over 2. Right? No, just plus epsilon. Cosine pi over 2 plus epsilon. So pi over 2 plus epsilon gives you the same as sine, right? With a minus, I guess. So it will be, yeah. And another will be with minus. So essentially the first term will just become minus 2 sine squared epsilon. This will be the first term. Just check it later. And then for these terms you get exactly minus 2 1 over 4 plus epsilon square pi square 1 over 4 minus epsilon square over pi squared cosine squared epsilon. So that will be the formula exactly. You can see that this term is positive, is bigger than 1, okay, because the numerator bigger than the denominator. So what you can see is that, just check, the trace of f will be smaller than minus 2 for small epsilon. Which means that modulus is bigger than 2, which means instability. Essentially what we proved is that when we go from the resonance point up, you will have, the system will be unstable. So that's small exercise, but this can be done in a general. So essentially what happens is that there is a whole region here which is unstable. There is a whole region here which is unstable. There is a whole region here which is unstable, and so on. So that's unstable. So to every point you have attached the instability region. I'll show you later in the computer exactly how they look like, but you can compute them, plot them on a well. There is you can make analysis, but also you can just on a computer verify this inequality and just draw where it's stable, where it's unstable. It's just simple inequality for the depending on A and B. You compute which is omega 1 or omega 2 and check if the trace is bigger than 1. Absolute value of the trace is bigger than 2 or smaller than 2. So that's how you make an analysis. And let's see what does it mean. Let's see what does it mean. What does it mean? So what means that the system become unstable? It means that you have an unstable system when A is approximately one force and B small. Right? So it's enough to have small b, but A close to one force to go to instability region. But A and B has some specific formulas. So A, one force, means that to B small means that you can just destabilize the pendulum with a small amplitude vibration of the support. But what is A1 force? So A1 force is this expression. So it means that G over L omega squared is approximately one force. So this, you put omega squared is approximately J over 4 J over L. This means that omega is approximately natural frequency of the pendulum multiplied by 2. So the omega n is square root of J over L. Remember, the square root of J over L is exactly the natural frequency of the pendulum. And what we say is that the first region of the resonance is when frequency of the support is twice bigger. And this is exactly the swing that we saw. So the first region of instability is which is the biggest one, is when when you move the support with a frequency twice bigger than the pendulum itself. So this is exactly when the pendulum makes half a period. You already have to make full period with the support. Then another half period, full period of the support. And this is that swing. So when you stand and sit, you have to do it with a twice frequency as a swing. So every time swing goes one side, you already made the full period of going up and down. When it goes back, you again make a full period of up and down. So that's a ratio. So the difference parametric resonance from the usual resonance is that the main region is when your change of the parameter with the frequency not close to the natural frequency, but twice bigger. Yeah, and this make it so not only natural frequencies are dangerous in this case, but also essentially the most dangerous frequency is twice. Yeah? And this is exactly what makes the pendulum that swing to rotate so efficiently. So that's kind of instability. Break. We have a lot of continue. Okay, so we continue. So several extra arguments about this these stability conditions. Which may be interesting is position of eigenvalues depending on the parameters. So let's draw this picture again. B and A. And we have the first point at 1/4, then at 1, 9/4, this resonance points, and then we know that there is this kind of instability regions. And at every point we know that there are some eigenvalues, right? There are some eigenvalues. We know that here we're stable, and if we're stable, at every point the two eigenvalues must be real and must be real. And here the two eigenvalues they must be complex conjugated. Right? Here the also eigenvalues must be complex conjugated. And here they must be real. So now there are two options for two real eigenvalues. Because product is 1, so either they're both positive or both negative. And this we can check. So essentially what we can see is that when A is 1/4, you see when A is 1/4, then trace A is 1/4, then A is 1/4, the trace is exactly -2. Trace is -2. Trace -2 means that at the boundary, at the stability boundary, exactly at the boundary, the two eigenvalues are -1. Right? So at these two boundaries are -1. That means that whenever you go out, the two eigenvalues should be real negative. Right? What I'm telling. No, it's all the way around. So they, in a stable situation, they are complex conjugated, right? So here they're complex conjugated. And here they should be real. But in that case, since they should match at -1, they are real negative. And in this case, they are real positive. So because in this region, you can say the trace is 2, which means that two eigenvalues at the boundary, exactly at the boundary, we have the situation with two eigenvalues +1. So actually these regions are not exactly the same. So this is instability, this is instability, this is instability. The regions are not exactly the same because in this region the boundary is characterized by double eigenvalue. So this is stability boundary. The trace can be +2 or -2. So eigenvalues can be -1 or +1. So in first region, the boundary is defined by eigenvalue -1. The second region is defined by eigenvalue +1. This is -1, +1, and so on. And in particular, what you can deduce from this is that whatever A, well, this is A, this is A, this is B, of course. Whatever B you take, these regions can never meet because one boundary carries two eigenvalues -1, another boundary carries two eigenvalues +1. So they cannot merge. And what happens is that as you increase B, they come very, very, very close, but never intersect. And this also never intersect. So this is one of the properties. So essentially, you can see how eigenvalues move. And if you go, for example, in this direction, you change A, you see that two eigenvalues are on imaginary, are complex, then they should, when you come to this point, they should merge at -1, split, become real, then they merge at -1 again, split, become complex conjugate, merge at +1, split, become real, merge again at +1, split, become complex conjugate, and so on. So you can see how the eigenvalues just move if you go through this diagram. This is kind of interesting thing. But another interesting issue is no. Before making another interesting issue, so let's do. Let's consider another system. So the Meissner equation, it has, of course, the property that we can solve it because the equation is piecewise constant, with piecewise constant coefficient. Coefficient is periodic, but piecewise constant. So at every time interval and it's constant, we can solve it. That's why we can find Floquet matrix explicitly and make the whole analysis. In usual applications, you don't have this situation. Usual application H, which is a position of the, for the pendulum, it's a position of the support, but there are all kind of other applications that lead to the same equation. But important is that H is just a cosine. So let's take with minus. It's just cosine. So in case of pendulum, imagine that you have a support, and then it goes up and down with amplitude delta and frequency omega. Equation is the same, and at the end you get you can make as an exercise that with just the same steps you get to the equation which has the form phi double dot plus A plus B cosine tau phi equals 0. So instead of h of tau, we now have cosine tau here. The only change in the equation, which for the Meissner we had h of tau. Now for this type of oscillations of the support, we have cosine tau. That's all difference. And this is what's called Mathieu equation. This was Meissner. And now we have Mathieu equation. So the rest of the analysis can be done exactly the same, with the only difference that we cannot anymore find matrix F explicitly. We can compute. You can compute much. You can also prove that the determinant is 1. You can prove all these conditions for the trace. So all the conditions you can prove. The only that you don't have that nice expression. You can only make it numerically or with some asymptotic analysis. So essentially, the same idea is that we also have resonance points where A is n squared over 4 and B equals 0. And the diagram is similar, but they're slightly different. So again, we have this one force, 1, 9 force, and so on. And diagram close to the points, it's somewhat similar, but then it's slightly different. So again, we have instability here. Unstable unstable. Situation is similar, so this is Matthew. Analysis is similar, so the advantage of Mason is that we can solve. In case of Matthew, we cannot solve. And the idea is the same. So essentially what you will see is that this is close, qualitatively close to what really happens. You can see that indeed the first region of the instability, which is close to 1.14, is the largest one. The others are much thinner. So if you want to really destabilize the pendulum, it's much better to be here than there or there, right? Because here you don't need to tune your parameters very well. So you just sit somewhere here, it's unstable. And 1/4 is that condition that the frequency of the support is twice frequency of the pendulum. So that's main region which corresponds to the relation that the frequency of parametric excitation is twice frequency that the system. So essentially, they're a very similar situation, but that's that equation that you will see much more often if you get to the application of parametric resonance. So the next observation is that stability. And what you can see here is that whenever we have stability, we are in a situation when the eigenvalues are exactly on the unit circle, right? So if it's exactly on the circle, we're with the Lyapunov special case. So Lyapunov special case means that though the linear stable, this equation is stable, but original equation for the pendulum, when there is a sine phi here, we don't know, we're not sure about this. So it may be stable or unstable depending on nonlinear forces. For the pendulum, when there is no excitation of support, we can prove that it's stable because of this energy, minimum of energy condition. Remember, we had to use a different way how to prove that it's stable. So here, it's also trouble. So this is a trouble because this is a Lyapunov special case. It means that linearized system is stable, but we cannot guarantee that nonlinear system is stable. So the one easy way how you solve this issue is using dissipation. So as you consider a small dissipation. This is a rather physically relevant way because dissipation is always present. So just let's add small dissipation and see what happens. So when you add a small dissipation, so remember how you add dissipation. So you add just coefficient with a third derivative, so that then the equation become with dissipation, like friction. For example, friction in the support or interaction with the air, whatever. So the equation become phi double dot plus this dissipative term. This is always was a term which was showing modeling dissipation in our systems, plus the rest. So this is damped Macy equation. Again, you can make the whole analysis in just the same way. You can compute Floquet metrics and then check where the eigenvalues are situated. You cannot do it analytically directly. You can make asymptotic analysis or numerical analysis. So what you find is that whenever you add delta, which is small positive delta, so this is a dissipation coefficient. So whenever you put small positive delta, instead of this angle, this you get, so the boundary or stability boundary will change, and it strictly goes inside. So it will be following rather closely this boundary and then goes up. Like this. So if the white was corresponding to delta equals 0, then this orange corresponds to delta positive. And whenever you put delta positive, what is inside this region is now asymptotic stability. So now inside this region, the eigenvalues will move inside the unit circle, which means asymptotic stability. No. What I'm talking. So it will be unstable, but what is outside? So now outside, will be outside the eigenvalues will move to inside. So if they outside, they were on the unit circle. So whenever you add damping, you can prove that they will move inside. So if the eigenvalues move inside, it means that we have a asymptotic stability. By the Lyapunov theorem. So what happens with this picture, whenever you add small dissipation, in the stable regions, the eigenvalues will move inside. So you get asymptotic stability, which is the same for linearized system and nonlinear system. So now you guarantee that it's stable here. We also, by the same theorem, guarantee that it's unstable here. And since delta is small, then these boundaries are close to these boundaries that we had before. So essentially, this is one of the simple ways how to circumvent this Lyapunov special case. So we don't, instead of studying nonlinear system, we just add small dissipation and see what will change. And we see that really the boundaries which we obtained with the linearized system are robust to adding dissipation. So actually, what is unstable remains unstable, but what is unstable remains stable. We just slight change near the boundaries. So and that's an important situation. So that's an important situation. So the way how you can, what you do in a special Lyapunov case, either you just go directly and start considering non-linear terms and see if it's stable or unstable. It's a very difficult problem here. Another way, also physical way, is add some small terms which you neglected. In that case, it's dissipation, and see what will happen. And whenever you add small dissipation, everything become already rigorous, because now the Lyapunov theorem is applicable. Okay, so then I will show you some videos and pictures which are essentially from the notes. But before I give you some theoretical part. So yeah, I did. It was better too. I didn't want to erase it. So it's a messy equation. Let's just repeat it. So I would like to show you one of the applications of the Massive equations. The massive equation is very old, so it's more than 100 years. Analysis is also quite old. And this analysis of Meissner equation is also like 100 years old. So everything is rather old, but and very clear, but you will see that by clever use of just of this equation, you can get a lot. And one of the applications is what's known ion trap. So this is application which comes from physics, where they want to control one particle. So you take one particle, ion, which means the particle which has charge. So you want to make experiment with just one particle. This is they usually like to do in quantum physics. So you need to take a particle, just one molecular, and put it in a certain place, and you should know where it is, and keep it there. And also, you want to know that what it is what you want to be there, because there are many molecules. You can just separate the ones that you want to study. So how to do it? The problem with the charged molecule is that you cannot stabilize it by the constant. You cannot just put electromagnetic field constant and it will be stable someplace. You can have the theorem that is impossible. So the way how you, for example, so what we will see is an example of the well. So we'll see how it can be done. So how it can be done? You take a particle with certain mass and charge, right? And you put two type of electric field. Yeah, so you put so it's charged, so you can put one electric field vertically and another electric field horizontally. So let's assume that we're in 2 dimensions. You will see picture in 3 dimensions. So you can put one periodic field here, or one field here, another field there, and you can change this field periodically. Right? So you can change this field periodically there, periodically here. So what will be equation of motion for this system? So let's put coordinate x here horizontally and coordinate y here vertically. And you can arrange the field, electric field. You can in principle do a lot. No? You can have a lot of freedom. So we will put electric field exactly such that x motion of this particle has a form of the Matthew equation in this form. So this is a force, right? So this is a force, and you put electric field such that it gives you constant plus b cosine. This is just by putting the certain form of the. You will see the exactly picture which give this. So you put electric field such that in horizontal direction, the field is oscillating. So and it gives you the force on the mass. As I said, that with a constant field you cannot do you cannot stabilize. So we try with non-constant force, non-constant field. And in y we do the same. In vertical direction we do the same, but instead of plus a we put minus a. Good. So now what will be stability of the system? The system will be stable if the first will be stable and the second will be stable together. If one of them is unstable, the particle will not stay here and will just fly away. Right? So it should be stable with respect to the first and with respect to the second. And the difference between the two is that A is either positive or negative. So this is what we didn't draw in this picture. But in fact, you don't need to have A only positive. You can have A negative. So the picture which continues is that you can only compute that there is instability also there. So you can extend this diagram to negative a, because there is nothing which forces us to give a positive. For pendulum, a positive, but in this equation, a can be positive, negative, and you see that there is instability there. Okay, so let's just draw the stability region for this equation. B and A. So for the first equation, the stability region is just what we draw with what we had here. There will be one force. Right? So stable is just in this region. And here it's unstable. And here it's unstable. And then this is x direction. And then we can draw the same in y directions, but it's minus a, so just we flip it in a. I always make it wrong. So it's a, this is b. So you just have to make it symmetric. Minus one force. Here it will be so it's stable here. So what you see is that the system is only stable in this region and in that region. I will just magnify this a little bit. So this is one force, minus one force. So what we have is that we have that, and that. So this is the region where we are stable. No. All wrong. So stability region stability region here of the red is here. Stability region of the purple is here. So the stability region is this. This is stability region. Okay, so that's simple. So stability region in this kind of romp-shaped area. So this is stability region. So whenever you're out, you're unstable. So now what happens with this equation? So what happens is that A. So we need to know what is A and B. So the same transformation as we did to come to the material equation from pendulum, the change of variables gives A as some constant, which was gravity in pendulums. Here will be some different constant divided by mass and omega squared. So that's an important difference. In the pendulum, we didn't have mass in the coefficient, but in ion, the force depends on charge, not on mass. So you get mass here. If you're interested, you can just check how these equations are derived, but I will not do this. But important is that A is some constant divided by mass omega squared. Remember, in our case with the pendulum, we had J over L omega squared, right? And here is some constant divided by mass again. So instead of for the pendulum, we had delta over L, but here's just constant by mass. So what it means that, for example, when there is no, it means that A and B, if you for all different particles, whenever you have different particles, they only change A and B. So are both inverse proportional to mass. So A divided by, for example, B divided by A will be B over A omega squared. You see, does not depend on mass. Mass, but depends on frequency. So what you do is you put by changing the frequency. So whenever you have a system, by changing the frequency, you can put you are on a straight line in B space, and what you do, you choose frequency such that you will be on a line which is exactly passing here. So you can choose frequency to be on any line. Yeah, because it's B divided by A is just inclination. And you choose other parameters such that the mass of your particle that you are interested to, because mass is how far from zero you are inside this corner. And other part you choose in such a way that the other particle that you're not interested will be outside. So in this way, if you put your system with these two fields, the only particles which will stay are exactly ions with exact mass you want. So all the particles that you're not interested in, they will fly away. And only those particles will stay there. So that's a simple idea. Which was developed starting from, I think, from 60s. And in 1989, it gave Nobel Prize to the authors. So what was Hans Demmelt and Wolfgang Paul. So they developed this idea, which is just directly based on material equation, and some more developed ideas when it's not necessarily should be ion, but with magnetic field. So then there are many natural extensions for these ideas, how to trap one particle of certain type in a certain place. Yes, and you see that it's just by playing with the stability diagrams and the parameters, you just put the system in such a state that only the particles you're interested in are unstable, all other are unstable. So they fly away. I'll try to see some videos, and then I need to give exercise. Today we probably a bit late. Essa segunda eu quero ver uns. Before putting. Well, this is just for lecture notes, just to give you some nicer pictures to what we did. You can look it in the, you can download it from the page, my webpage. So essentially, this is how the instability regions, you see, for the Messner equations, they start from, these are numerical simulations. So this is start with 1 force, from 1, from 9 force, and this is A and B. So you see that there are tongues coming out. So the thickest, biggest one is from 1 force, is from this main resonance, when the frequency of parametric excitation is twice natural frequency. So this is the biggest zone where everything usually happens. This is just to show you when B is very large. Bit is B. So B is very large, so there's these thin zones appear, but then something happens. Well, the only interesting is that to see that the boundaries of the adjacent zones, they never intersect. So these lines are two boundaries that coming close, but boundaries of the same zone can intersect. So this is because the eigenvalue is -101. So this is a picture for the zones of the Matthew equation. So just what I draw on the right picture. So there is a first zone on the 1/4, second zone, third, and they become thinner, thinner, and thinner. And then there is this zone for negative A. This picture shows what happens if you add dissipation. You see delta 0.01, 0.05, and so on. So the zones of instability just become slightly smaller every time you add a dissipation. And the white zone is the region of the asymptotic stability. So the eigenvalues here are inside the unit circle, and here there is one outside the unit circle. And then this is a picture of this ion trap. So you put one electrode from above and from the top. This gives you equation for y variable. And from then there is a circular electrode on the side, which gives you x variable. And then you inject ions, and only the right ions with the right mass can stay. All the rest will just escape. So this is how it works. And so the next is we have to give. I want to give you exercise. So exercise is the following. So exercise. Remember. So as I said, that this picture corresponds to the pendulum where you put support vibrating. And in this case, A was J over L omega squared. So it's positive. But when you see that it's positive, you can think of it's positive because gravity is positive. So what happens if gravity is negative? And gravity is negative is for the inverse position of the pendulum, upper position. So if J is, in that case, J become negative, A become negative. So you're here. So the question here is that there is on the inverted pendulum, there is also instability region, which is typical normal, because, for example, if there is no perturbation at all, B is 0, you're unstable. This is, we know that vertical position or inverse position of pendulum is unstable if you just don't touch it. But you see there is a stability region. There is a stability region, and the stability region, to enter the stability region, you should have A very small. You see, because stability region is when A become close to 0, because this is A axis. In order to have A close to 0, it's enough to have frequency very large. See, by having frequency very large, you can put A 0, and then you get in stable region. So what this picture tells that for A very small, we have stability. For A negative and very small in absolute value, we have stability. What does it mean? It means that if you take pendulum in the vertical position and start to vibrate the support with sufficiently large frequency, it becomes stable. And this is I want to show you, and this will be actually the exercise. So this is, well, that's some experiment from the videos I brought from this laboratory of nonlinear dynamics in Tsukuba, done by Professor Hiroshi Yabuno. And this is a, let's see if it works. Not yet. Yeah, so it's a pendulum, and this, you see it's false. It's in a vertical position, it's unstable. Now if you put sufficiently high frequency, it just becomes as stable as the lower position becomes unstable, but upper position becomes stable. Just like changing the gravity up and down. And that happens with many systems, including the, if you just take a trunk of water and put ball, in some situations what happens that the light balls will go down and the heavy balls will go up. So many things with this high frequency excitation may happen. I don't want to get into this deep into this subject because we have no time, but I will give you exercise. So this will be 4. This is not sufficient. Well, as usual, it will be for the next Monday. So next Monday, today is number 6. Sunday 6, so it plus 7. 15 February. Just now, for who is late but still want to send the exercises that we did before, please send. Okay, so late is will not be strongly punished. So what we do, we consider the pendulum in the upper position. And we consider pendulum which is moved up and down periodically. So what do we have in this case? In that case, we can consider in principle the same equation of motion. If we compute phi from below. And then the upper position, upper equilibrium, will correspond to angle pi. So that's either you just directly compute it from the upper position as we did before, but let's do it in that way. So we take usual equilibrium pendulum equation and consider it around the upper position. Then we have to linearize with respect to small deviation, right? when you take when you take small deviation, in that case, sin phi, you have to expand not around 0 but around pi. So this will become minus delta phi, because derivative at pi will be minus 1. And then you get linearized equation well, essentially just putting minus. Take this equation. And we use the same perturbation as in Meissner equation. Same perturbation is in Meissner. So the first problem is to show that in coordinates in time in that new time where omega, remember, is 2 pi over t, we have the Meissner equation. We get Meissner equation, but with a difference. A now is minus g over L omega squared, negative, and B is the same. He'll show that, just make this simple transformation of time that we did, but just to see that instead of A will change the sign. So we only, second, because in that case it will be minus A and minus B. So in order to make change B to positive, you add half a period here. That's good. So add a half a period, and this gives you, yeah, I think this, well, check. Well, in order to make it, to have B positive, I will put just plus here and minus here. Okay, then it solves the problem. So it will be just the same H capital. Okay. You get, so the idea is that you get Meissner equation, but with negative A. That's the only difference. So for inverted pendulum, you get negative A for the Meissner equation. So the next step, you should write equation so you exactly in the same situation as we did before, but so you can do the same analysis. You can, in the second step, you find F-loci matrix. Just in the same way, by splitting a system into two pieces. So the first system will be at the interval between 0 and pi, right? And this will be a system with when and you consider the special case when A smaller than B. A smaller than B. So when A is smaller than B, you can find that omega 1 squared is still positive. A plus B is still positive, but A minus B is negative. A plus I wrote it in the morning and it seems to be a bit this is a bigger, so it means that B is bigger than modulus A. No, the way around. Yeah, that's okay. So A is small. A is small, and A is small is always, it can be achieved by making fast frequency of the oscillations, because frequency is in the denominator. So what you do, you again write the equation of motion and in the two half periods. So in the first equation will be phi double dot plus A plus B, right? Phi. In the second half period, phi double dot plus A minus B, phi equals 0. And the difference that since B is small, is large, so that will be positive, and that will be negative. So then you can write this as phi double dot plus omega squared phi equals 0, where omega squared is A plus B. And this gives you phi double dot minus sigma squared phi, where sigma squared is B minus A. So you get, instead of two equations where you say, the first you solve as cosine and sine, but second you solve as sum of exponents. So this is the difference. So it gives you the same matrix F1, but the different matrix F2. So this gives you the matrix F2 with exponent, and this gives you matrix F1 with signs. So the first matrix will be just the same. The second F2 will be different. Then you can write stability condition. So essentially, this is if you check the determinant of F1 is determinant of F2 is 1. You can check the determinant is still 1, then the stability condition is just the same as we did before. Right? Our stability condition was based on the fact that determinant F1 and determinant F2 equal 1. So then stability condition depends on just on a trace of matrix F. So you can derive what is trace by having these two matrices F1 and F2. So there will be different trace. So at the same, you get the condition that the trace of the matrix should be smaller than 2, yeah, for stability. Well, this is difficult exercise, yeah, so it's quite a lot of work. And 4, show that that the system is stable if A, which is J over L omega squared, is small enough. I guess this should be possible. There will be condition. The stability condition will be just the same. It's the determinant modulus of trace f smaller than 2. You can compute f, and you check that it's satisfied whenever a is small enough. And this exactly shows that the inverse position of the pendulum becomes stable if a is small enough, which means that if frequency is large enough. Well, try. This is one of the hardest probably exercises, but there's nothing else that following what we did today in the lecture. But there is just the only difference with the matrix F2. Yeah, so you see how it will affect the final formula. Okay, good. So see you. So now from tomorrow we start with waves, and so we have still 5 lectures with.